uh, is by Geetanjali Sarkar. I hope I pronounced your name correctly. And Raghvendra. And so I'll give you the 1 minute to the 12-minute length, and we'll okay,
Thank you.
shout it out. Go ahead.
Hello, everyone. Today, I'll be talking about the modeling of dust emission from post-red giant branch stars in the Large Magellanic Cloud. And I will discuss this in the context of common envelope mass ejection in evolved stars. This work has been done in collaboration with Raghvendra Sahai, and the paper is available on the archive. So I begin with some spectacular images of the Boomerang Nebula. Now, on the left, we see an HST image of the Boomerang Nebula, and on the right, we have an ALMA image of the nebula superposed on the HST image. In both the images, we can see that we have beautiful bipolar lobes, and one would expect that the central star is a post-AGB star. However, the luminosity of the central star in the Boomerang is just about 300 L sun. So that puts the Boomerang on the post-RGB scenario. So we have a new evolutionary class, the dusty post-RGB stars. And the Boomerang Nebula is the only example of such objects in our galaxy. These have been studied extensively by Sahai and collaborators. So recently, Devika Kamath, Peter Wood, and Hans van Winkel identified several dusty post-RGB stars in the Large Magellanic Cloud and the Small Magellanic Cloud. To be precise, 119 in the LMC and 45 in the SMC. Study of objects in the Magellanic Clouds removes the distance ambiguity and enables reliable luminosity determination of the objects. Kamath et al. Found that the effective temperatures, log G, and metallicities of these objects are similar to post-AGBs. However, they have much lower luminosities, less than 2,500 times L sun. Also, unexpectedly, the spectral energy distributions show evidence for circumstellar envelopes, shells, and/or disks, which are similar to post-AGBs. So what caused the premature termination of the red giant branch, and what is responsible for this infrared excess? The only plausible explanation that we can think of is binarity and common envelope evolution. And to put it very simply, common envelope evolution is when the red giant in the binary overflows its Roche lobe and the accreting star is unable to take up the transferred mass all too quickly, and a common envelope results. Now, the common envelope evolution can have two scenarios. There can be an episodic mass ejection, which leads to the circumstellar shell, as discussed by several people, such as Clayton et al. In 2017. The remnant gas might fall back and interact with the binary, leading to circumbinary disks, as we can see, for example, Kashi and Sarkar in 2011. There can also be another scenario where the common envelope is not ejected episodically, and instead we have the in-spiral of the binary, which simulates results similar to pulsations in AGBs, leading to efficient mass loss through dust-driven winds. This was put forth by Glantz and Peretz in 2018. So with this background of understanding the dusty post-RGBs, I now go on to the dust modeling of these objects. Kamath et al. Classified these sources as either shell type or disk type, depending upon whether the spectral energy distribution peaks redwards or bluewards of 10 micron. We picked up a sample from their 2015 paper of dusty post-RGBs in the LMC. We chose 4 shell type and 4 disk type post-RGBs, and we made sure that the luminosities are less than 1,000 times L sun, so that there is no confusion that these objects are indeed RGBs, post-RGBs, and not post-AGBs. And for comparison, we also modeled 4 shell type and 4 disk type objects, post-AGB objects, and the luminosities of these was always greater than 3,000 L sun. Our spectral energy distributions extend from the U band to 24 microns. For modeling, we use the one-dimensional dusty code. The free parameters, there were 5 of them: dust temperature at the inner shell or disk boundary, dust grain sizes, the grain compositions, the optical depth, and thickness of the shell. Since it is a one-dimensional code, the disk was approximated as a wedge-shaped fraction of a sphere. So I discuss our results with 2 examples of modeling of 2 post-RGBs. The first is J050257, and this source we tried a one-component model. It is a disk source, and we can see that the model is deficient in the mid-infrared region. A 2-component model which incorporated the disk gave a good fit to the spectral energy distribution. Next, I show you J051920. This is a post-RGB shell source as classified by Kamath et al. And again, a one-component model fit was deficient in the mid-infrared, and we required to incorporate an inner disk to obtain a good fit to the spectral energy distribution. So we may conclude that the classification of these sources as shell type or disk type is not very robust. We found circumstellar shells in all the objects, but some disk sources did not show the presence of a disk, and some shell sources showed the presence of an inner disk. Surprisingly, we also found that the ejected matter may be carbon-rich in some sources. For example, the post-RGB source J055102. Here, the disk was found to be made up of amorphous carbon grains, and the shell had silicates and silicon carbide. Now, this is rather surprising. We do expect circumstellar shells rich in carbon around post-AGB stars, which have gone through the third dredge-up, but we wouldn't expect this around oxygen-rich post-RGB sources. So the only plausible explanation would be if this object is a CH giant in a binary system, which may have accreted matter from the more massive AGB companion earlier on, before the common envelope ejection. We also find that discrepancy between model and observed SEDs in the 5.8 to 8 micron region may suggest polyaromatic hydrocarbon emission. Again, PAH molecules would not be expected in oxygen-rich envelopes of post-RGBs, so this would also support a binary hypothesis for these type of objects. Now, one might say that UV flux is important to excite the PAH molecules, but Lee and Drain in 2002 showed that actually UV flux may not be imperative for PAH excitation, and stars with effective temperatures as low as 3000 Kelvin can also give rise to PAH excitation. I now summarize some of the other parameters that we derived from our models. We could of course get the dust temperatures at the inner boundary of the dust shells, the opacities, the grain sizes, the luminosities, and more importantly, we could estimate the total mass, gas plus dust, in the circumstellar shells. So we now place these model circumstellar dust masses on a plot of theoretically estimated dust masses in the ejecta of post-RGBs resulting from common envelope evolution as a function of initial stellar mass. This plot was taken from Liu et al.'s paper in 2013. We put our objects here, and we find that our objects mostly lie between 2 solid curves. The lower curve corresponds to the base of the first giant branch or red giant branch, and the upper solid curve corresponds to the tip of the first giant branch. So we can see that for the post-RGB sources in this study, common envelope evolution occurred most likely near or at the tip of the RGB. So I must summarize my conclusions as: on an average, shell masses in post-RGBs are less than in post-AGBs, is what our study revealed. But there's a caveat here. Substantial mass may lie longwards of 24 micron. We are limited by our data, observational data. The disk fractions we found are typically large, 0.3 to 0.4, implying that the disks are geometrically thick flared structures with substantial opening angle. For some post-RGBs, the dust may be carbon-rich. Published classification of these objects as shell or disk sources is not robust, is what we concluded. And finally, the comparison of our model dust masses with theoretical models suggests that common envelope evolution occurred near or at the tip of the RGB. Further progress in our understanding of these dusty post-RGBs will require HST data to constrain the morphology and dust density as a function of radius. We will also require JWST spectra to determine dust composition and better define the spectral energy distribution, and ALMA observations to determine the gas mass. Thank you.
Thank you very much. Tommy.
Thank you. These are fascinating objects. Can you hear me? Hello?
Hello, yes. Thank you.
Oh, okay, yeah.
Yes.
So I have a couple of questions. The first one is, why do you insist that those C-rich post-RGB stars are not actually post-AGB stars? What is the reason you still believe they are wrongly classified as post-RGB?
The main reason being that they have very low luminosities. Some even have luminosities less than 100 times L sun. So the low luminosities cannot place them on the post-AGB phase.
And extinction is not, it cannot be blamed on this.
I'm sorry, I didn't get you.
Extinction, like which is like a free parameter in your models, that there is no modeling error
No, it would not cause so much of a difference. In fact, Kamath et al. Also estimated luminosities, and from there, analyze the dust strictly as such, but they obtain low resolution spectra and derived luminosities. Our luminosities are in good agreement with them, and it would not make an order of a magnitude difference, like from 80 to maybe 3000. That is a lot of difference. So I don't think extinction can cause that much of this thing. And okay. I mean, it's very unlikely that these are post-AGBs.
I see. Okay, and the second question is that I can imagine that the common envelope systems can eject the common envelope, and it may be gaseous or dusty. But your objects seem to be very dusty. Does it constrain anything about the nature of the companion? Is there like a temperature limit on the effective temperature on the companion that those systems involve?
Sorry, at the moment we have no clue about the companions. We can only guess. For example, when we see the carbon-rich circumstellar environment, we guess what the companion could have been. We expect these objects to have to be very close binaries. So I'm not sure how much they would even get resolved by HST. But maybe we could at least get an idea. If we take the HST images, we could have some information about the disk, the nebulosity, extent of the nebulosity, etc. But as of now, we have no clue about what type of companions they could have and what type of a binary system these would be.
So the fact itself that those objects are very dusty, that doesn't tell us anything about the companions.
No, not really. I mean, if I get your question correctly, we don't get much information about the companion except that these objects have been found to, Kamath et al. Have been doing some photometric monitoring of these objects, and they have been found to be, showing small photometric variability. But from the dust as such, from my data, I cannot infer anything about the companion as such. Probably more observations would tell us something else about it.
Okay, thank you.
Noam.
Yes, very nice. Now that you observe the system presently, the central star is already, what type of central star you have? It's already horizontal branch star?
No, these would have just not horizontal. It may be on the horizontal branch, yes, but we have analyzed a very small sample to begin with, and yes, they could be on the horizontal branch. But it would also depend on the metallicities of the objects, and the horizontal branch stars. I mean, it's very difficult where exactly at the tip of the RGB, just after the RGB, or where it is. I think we need we need to do more spectroscopic studies of these objects, and then we can get some information about.
But they are post-RGB, you said.
Yes, we say they are post-RGB.
No, so I have a short comment, because in the last year, we tried to understand the formation of common envelope on the tip of the RGB, and we propose, I admit, it is a very speculative scenario, that during it's only for low mass stars. If you have core helium flash, we examine what happened if the very strong convection in the core excite G waves and then P wave that expand to the envelope and can cause envelope expansion by a factor of 2 or 3. And then if you have a companion that until then did not interact with the RGB star, it will then interact, because for a short time, for several years, the envelope expand a lot by this energy deposition. So this might explain the tendency of strong binary interaction just at the tip of the RGB. But I admit it is a speculative scenario.
Also, from what I gather from literature, for very small mass stars, I mean, maybe close to 1 solar mass or less than 1 solar mass, just at the beginning, maybe like which are expected to go through the RGB, the mass loss would be much more dramatic than what we would expect, say, in the mid-range. So maybe for 3, 4, 5 solar mass object. So yeah, I mean, I could look at your paper and see.
Okay.
Thank you, Miguel.
Sorry. Yeah. Here in your conclusions, you put like Polish classification of these objects as shell or these sources is not proposed, but sorry, I don't fully understand what you mean with proposed.
Okay. See, they may have an inner circumbinary disk, and which would be which has a certain thickness and a outer shell. Now, if we do not see a mid-infrared excess, if the peak of the spectral energy distribution goes towards the far infrared, on the face of it, Kamath et al. Thought that these were just shell sources, in the sense that they did not expect that these objects would have a disk component to them. But when we analyzed the data, we found that although they are peaking towards the far infrared, our limit is 24 microns, they still require, some of them do require a disk for a better fit in the 5 to 8 micron region. So that's where we think that a disk, we estimated the disk by assuming that it is a fraction of the sphere, so it is taking up a part of the bolometric flux, and then the output of the disk is then going onto the shell and illuminating the shell. So I don't, if I could explain that, yes.
Yeah, that's good. Thanks.
Thank you. I think we can move on to the next speaker, Luke.